Hi, welcome to the Radio Joe Project Citizen Science Training Modules and the Sunrise Ground Radio Lab. My name is Dr. Samantha Blair and I teach physics and astronomy at Dalton State College. I also am a member of the Radio Joe team. These training modules are a partnership between the Sunrise Mission Team and the Radio Joe Project. We acknowledge contributors to these modules as well as our funding sources of support without which we could not do these projects. And this is training module 0.2, and in this training module we will talk about the solar atmosphere. Prerequisites for this module will be, the general science, understanding the electromagnetic spectrum, understanding speed, wavelength, frequency, and energy, being able to read a graph, and hopefully you have gone through training modules 0.0 and 0.1. What you're going to learn about in this training module is about the structure of the sun and the features of the solar atmosphere. So once again, and in the last module, you also saw this same diagram. This is a cutaway diagram showing the various layers of the sun. The interior has the core, okay? The core is where the nuclear reactions occur, the fusion reactions that produce the energy in the sun. And then right outside the core, you have the radiative zone, and then going to the surface of the sun, you have the convective zone where radiation is, energy is transported via convection. The surface of the sun, once again, is called the photosphere, and this is where the gas becomes optically thick, which means it is opaque to visible light. That's why when we're looking at the sun, we're actually seeing the photosphere because light can't penetrate, so we can only see to the photosphere. Now, sunspots occur in the photosphere, and we're going to be talking about those. Above the photosphere, we have thin layers of the chromosphere and the transition zone, and then we have the very thin, hot, tenuous outer layer, which is the solar corona, okay? And the solar wind, which is a stream of charged particles that leave the sun, the solar wind is created in this outer layer of atmosphere of the sun. Now, the photosphere has a number of features in it, one of which is what we call the quiet sun. Granulation is part of the quiet sun. And once again, if you look at the photosphere in low resolution, you won't see this, but in higher resolution, you notice this grainy pattern on the surface, or what we call granulation. And granulation is a function of convection currents right below the photosphere, which hot blobs of material or gas are rise, and then they cool and descend. Hot air rises, cool air sinks, hot water rises, cooler water sinks. This is the way fluids behave. The blobs here that you see are about the size of Texas, all right, or 1,000 kilometers in size. And once again, if you look at the image of the sun, you can see that the center is brighter because we're looking deeper into the photosphere, and the outer edges are darker because we're seeing the cooler gas on the outside of the sun. Now, the image below is a sunspot, okay? It's a sunspot under high magnification. And as we were talking about, the darker, cooler regions sink in the granulation. you see the center of a sunspot is dark. All right, there are two regions to the sunspot. You have the very dark umbra, it's in the very center, and then you have the penumbra, which is the lighter region around it. Okay, and then you've got the regular granulated photosphere around it. So these sunspots are cooler regions of the photosphere. Okay, they're cooler than the photosphere surrounding the sunspot. Now, what causes sunspots? What are associated with sunspots? All right. Well, a direct proof that magnetism, or the solar magnetic field, is what is responsible for sunspots is this beautiful diagram right here. I absolutely love it, all right? The study of the spectrum of the sun under high magnification. So solar spectral absorption lines are seen in regions inside and outside of sunspots. So we have an iron line here, and you can see the iron line above and below the sunspot and then right over the sunspot. The Zeeman effect shows that in the presence of intense magnetic fields, spectral lines will split. And right here, we're seeing the iron lines split into three. All right, this is the Zeeman effect, which shows that in the presence of the sunspot, the iron line has been split into three, so we're seeing intense magnetic activity here. Okay, so this is a way to measure the intensity of the magnetic field inside sunspots, all right? And it's also a way to show us that sunspots are caused essentially by intense magnetic activity. Here is the sun seen in H-alpha emission, which shows many features in a layer above the photosphere called the chromosphere. Now, chromo means color, all right? So we get this reddish color, and it's because of the H-alpha emission. It gives off in the red part of the spectrum. And so there's several features we can see in the chromosphere. The white regions are called plages, and the dark lines are called filaments, all right? Both are occurring in the chromosphere, which is above the photosphere. And we also see what are called spicules, the small flame-like structures coming off of the sun in the region of the chromosphere called spicules. They're very pink or reddish, and they're really quite beautiful. You get a chance to look at them. So this is the chromosphere, the atmospheric layer above the photosphere. Here you can see the spicules that are coming up off of the chromosphere. You can see them more clearly, all right. You can also see the spicules during solar eclipses under high magnification. And here you can see them in motion. Now, another region of the solar atmosphere is something called the transition region. And as you see on the graph to the right, we have temperature in Kelvin and we have height in the solar atmosphere. We have the photosphere, the chromosphere, and then we jump in temperature in the transition region. And if you look at the left, the transition region is a very thin region where the temperature changes from thousands of degrees to millions of degrees. So we're taking a huge jump in temperature between the chromosphere in the transition region up to the corona. Now, the solar corona is a very beautiful feature of the sun that you can only see during total solar eclipses. It's the sun's very outermost atmosphere. It's a very hot, low-density gas, all right? It's very thin and transparent, and it's sort of like, it's called corona or the crown of the sun. We're not 100% sure about the energy conversion. We don't understand it 100%. A large temperature transition happens between the 4,000 and 8,000 Kelvin chromosphere and the million Kelvin corona, all right? This highly energetic gas is too thin to see under normal circumstances, but we can visualize it when the moon is covering the sun, all right? And these images show streamers of hot gas in the corona sculpted by the magnetic field of the sun, and it's an important clue to understanding the solar magnetic field. Now, this corona also forms the solar wind, and the solar wind's a high-velocity gas of protons and electrons that stream off the sun, all right? The sun is losing mass because of this. This is a part of a poster from a NASA Goddard Space Flight Center conference poster, which is summarizing the solar wind, a constant stream of charged particles and magnetic fields from the sun. The solar wind interacts with everything in our solar system. We can see it interacting here with comets, all right? We can see it interacting with planets and planetary atmospheres. It interacts with asteroids and everything, all right? And so planets that have magnetic fields are able to shield themselves from this ionizing radiation from the sun. Those that aren't able to. So if you don't have a magnetic field to protect you, you're going to get hit with that ionizing radiation from the sun, essentially, all right? So in particular, planets with atmospheres and magnetic fields can be heavily affected during times of strong solar events. And we get the aurora borealis and the aurora australis, and all planets with magnetic fields have these aurora events because of this magnetic field and the event of solar wind. This is another part of a poster from a NASA Goddard Space Flight Center activity summarizing the solar wind, a constant stream of charged particles and the magnetic fields from the sun. The solar wind interacts with all planetary objects. In particular, planets with atmospheres can be affected. And here we see the Earth and the moon, okay? And we got to think about our astronauts. Our astronauts can be affected by the solar wind as well. It just depends on where they are and how protected. It depends on where they are as to how protected they are by our magnetic field, okay? If we get too big an event coming off the sun, it can disrupt our communications, electronic communications, so forth and so on in our atmosphere, depending on the amount of material that's being sent our way from the sun. And so this concludes our material on the solar atmosphere, the layers of the atmosphere, and then some of the material that comes off of the sun, you know, regularly that can affect the planets and other regions of the solar system. Here's some resources, once again, on solar physics, if you're interested in looking further into any of these details. Thank you, and I hope you enjoyed this module and that you will enjoy the next module.